A single metal has powered cities, shaped global power, and now could determine the future of artificial intelligence. Uranium isn't just part of history anymore. It's quietly becoming one of the most important resources in the modern digital world. And here's where it starts to feel heavier than it sounds. Uranium is a naturally occurring element with the symbol U and atomic number 92. It's incredibly dense, nearly 19 times heavier than water, one of nature's true heavyweights. But what makes uranium different isn't just its weight, it's what's locked inside. Because inside every uranium atom lies something far more powerful than its physical form suggests. Energy, massive amounts of it. The kind of energy that doesn't just power machines, but entire cities. And that's where the story begins to shift, from simple chemistry to global infrastructure. Back in 1789, a German chemist named Martin Heinrich Klaproth discovered uranium while studying a mineral called pitchblende. At the time, it didn't seem revolutionary, just another element added to the growing list of scientific discoveries. For decades, uranium sat quietly in laboratories, misunderstood and underestimated. No one knew what it was truly capable of. But that changed in 1896, when physicist Henri Becquerel discovered something strange. Uranium was emitting energy on its own without any external trigger. It wasn't just a metal, it was active. That discovery opened the door to an entirely new field of science, radioactivity, later expanded by Marie and Pierre Curie. And with that, scientists realized something profound. Atoms weren't as stable as they seemed. They could break apart and release enormous amounts of energy.
It is an atomic bomb. It is a harnessing of the basic power of the universe. The force from which the sun draws its power has been loosed against those who brought war to the Far East.
And that's where uranium becomes something else entirely. Not just an element, but a source of power. Uranium exists in different forms called isotopes. Most of it is U-238, stable, abundant, but not very useful for energy production. But a tiny fraction, less than 1%, exists as U-235. And that's where everything changes. Because U-235 has a unique property. It can split. When a neutron hits a U-235 atom, it breaks apart in a process called nuclear fission. And that split releases an enormous burst of energy, along with more neutrons. Those neutrons go on to hit other atoms. And just like that, a chain reaction begins. 1 becomes 2, 2 become 4. And within seconds, trillions of reactions release energy at the same time. The scale of that energy is almost impossible to imagine. A single uranium fuel pellet, small enough to hold between your fingers, can produce as much energy as tons of coal. Tiny material, massive output.
Of this area have already been mined. You can tell because if you look up at the ceiling, you can see where the jet boring system drilled upwards to access the ore. And now, because they got all of the ore out of that cavity, it's been backfilled with concrete. Now, Cigar Lake developed a specialized jet boring system to access this very high grade of uranium. The system runs along these tracks so that they can move it along the length of this tunnel.
And this is where uranium steps out of theory and into the real world. Inside nuclear reactors, uranium is packed into fuel rods. When fission occurs, it generates heat. That heat turns water into steam. The steam spins turbines, and those turbines generate electricity. Simple in concept, but massive in impact. Entire cities can be powered using a relatively small amount of fuel. And unlike fossil fuels, nuclear energy produces extremely low carbon emissions, making it one of the cleanest large-scale energy sources available today. But there's something even more important. Nuclear energy doesn't stop. It doesn't depend on sunlight. It doesn't rely on wind. It runs continuously, providing what's known as baseload power. Stable, reliable, always on. And in today's world, that reliability is becoming more valuable than ever. Because the world is changing, not just in how we consume energy, but in how much we need. We're entering an era defined by artificial intelligence. From chatbots and recommendation systems to image generation and automation, AI is rapidly becoming part of everything we use. But behind every AI system, there's something most people never see. Data centers. Massive facilities filled with servers, processors, and storage systems, running non-stop to power the digital world. And these data centers are growing fast, faster than most people realize. But here's the part that's often overlooked. AI doesn't just need data, it needs energy, a lot of it. A single AI query can consume significantly more energy than a traditional internet search. Now multiply that by millions, then billions of interactions happening every day. Suddenly, the demand becomes enormous. Some estimates suggest that future AI systems could require power on the scale of entire cities. And data centers themselves? They're starting to consume electricity at levels comparable to small nations. And that's where the real challenge begins. Because while demand is exploding, our current energy systems are struggling to keep up. Renewable energy like solar and wind is growing rapidly, but it has limitations. Solar doesn't generate power at night, wind isn't always consistent, and data centers? They can't afford to shut down, even for a second. AI systems don't pause, cloud services don't sleep, they require constant, uninterrupted power. And that creates a problem the world is only just beginning to understand. A power gap, a growing mismatch between the energy we can reliably produce and the energy modern technology demands. And this is exactly where the story comes full circle, because solving this problem requires something very specific: high density, reliable, always-on energy. And right now, very few energy sources can deliver that at scale. And this is where things take a decisive turn, because the companies building the future of AI have already seen this problem coming. And they're not waiting, they're acting. Some of the biggest technology companies in the world are now moving directly into the energy space, not just as consumers, but as decision makers. Microsoft, for example, has taken a bold step by securing long-term nuclear energy agreements to power its expanding data centers. In fact, it's going as far as helping restart previously shut down nuclear reactors, simply to ensure a stable, uninterrupted energy supply for its infrastructure. That's not a small move. That's a signal.
The is up 100 meters above us, and we pile it down, and we hook up a 10-foot reamer, and that thing will pull that reamer up, and that'll make cuttings as it's going up. It's like a tunnel boring machine, but it goes vertical. They're in the...
Google is approaching the same challenge from a different angle. Instead of relying on existing infrastructure, it's investing in the future of nuclear itself, specifically small modular reactors, or SMRs. These are smaller, more flexible nuclear systems designed to be built faster, deployed in multiple locations, and scaled as demand grows. Exactly the kind of energy solution data centers need. Reliable, compact, always on. And then there's NVIDIA, a company at the very center of the AI revolution. Its processors power some of the most advanced AI systems in the world. But according to its leadership, the biggest limitation to AI growth isn't chips, it's energy. NVIDIA has openly stated that power availability could become the single biggest bottleneck for the entire AI industry. And that changes everything, because when companies like these start aligning around the same problem, it usually means the shift has already begun. And at the center of this shift is nuclear energy. Unlike solar or wind, nuclear power delivers exactly what modern infrastructure demands: consistent, high output, 24/7 electricity. No interruptions, no dependency on weather, no fluctuations, just continuous power. And that brings us back to uranium, because none of this works without it. Nuclear reactors don't run on concepts or code. They run on fuel, and that fuel is uranium. As demand for reliable energy increases, uranium is no longer just a background commodity. It's becoming something far more important: strategic. Governments are beginning to secure long-term supply chains. Energy companies are locking in future contracts, and investors are starting to pay attention again, not because of hype, but because of fundamentals. For years, uranium demand remained relatively stable. But now, something has changed. This new wave of demand isn't tied to economic cycles. It's tied to technology, to artificial intelligence, to infrastructure that must run, no matter what. And that kind of demand doesn't just fluctuate, it builds. At the same time, supply isn't scaling as fast. Uranium production is concentrated in a few regions. Processing and enrichment capacity is limited, and geopolitical tensions are reshaping global supply chains, which creates a simple but powerful imbalance: rising demand, constrained supply. And historically, that combination tends to lead to one thing: repricing. But this isn't just about markets, it's about systems. Because what we're really witnessing is a deeper transformation, a convergence. Artificial intelligence is driving energy demand. Energy demand is reshaping infrastructure. And infrastructure is bringing nuclear power back into focus. And in the middle of it all, uranium becomes the quiet foundation. Not visible, not talked about every day, but essential. From powering reactors, to enabling data centers, to supporting the digital systems billions of people rely on. Its role is expanding in ways most people haven't fully realized yet. Uranium has always been powerful, but today its importance is evolving. It's no longer just about electricity generation. It's about enabling the next era of human progress. Artificial intelligence, global connectivity, digital economies. All of it depends on one simple thing: reliable energy. And as the world pushes deeper into this new era, one question becomes impossible to ignore. Can our energy systems keep up with our technological ambitions? Because if they can't, the growth of AI itself could slow down. And that's why this moment matters. Because for the first time in decades, uranium isn't just part of the conversation again. It's at the center of it. The future of intelligence may depend on the power we choose to build today. And right now, uranium is quietly becoming one of the strongest candidates to carry that future forward. So the question isn't whether demand is coming. It already is. The real question is, are we ready for the scale of change that comes with it?